Okay, so for 2.24c, we did this in class, but basically we can assume steady state, constant thermal conductivity, one-dimensional varying only in the radius, conduction only. And because we know it's conduction, we have a certain Fourier's law we can use for what Q equals, and we know Qin equals Q out, or Qin minus Q out plus energy generation equals 0 because it's steady state. From there we can simplify like terms, take the limit as the change in radius goes to 0, and we get this boxed in answer. So then for 2.66, we're assuming heat conduction steady, one-dimensional, thermal conductivity is constant, no heat generation in the plate. So we know we can take the integral twice to get our C1 x plus C2, and the main bulk of it is finding what our C1 and C2 is. We find that C1 equals our heat generation over K, and our C2 equals our initial temperature, and we can plug that all into our Tx, or our value of temperature with respect to x, and we get this equation down here. And then for 2.102, the resistance wire, so heat transfer is one-dimensional, constant, heat generation is uniform. We have this equation derived that we just derived above. We can use that to find the convection at the outer surface, and we also know thermal symmetry around the center line. We can set this equal to 0, and we're basically solving for our C1 and C2 with the boundary conditions of at r equals 0, C1 equals 0, and r at the specified radius for a variable. And then we can just plug that into an equation that we already know and simplify. And then for 1440, for a Henry's law, assume air, if air is saturated, we know our saturation pressure, our partial pressure, we can easily solve. And then for dry air, we know the wet air, so we'd subtract that, get our certain answer, and then divide by our Henry's constant that we know equals this.